If you're still trying to finish up the first playground, you can keep that guy open and either come back to it or just sort of poke on it. For everybody else, go ahead and open up the second one, which is 2_Swift objects. And so the first thing in this, a couple of you asked about it. So if you've programmed before, you had questions about like, well, you know, what type of object is this? And Swift does this, I have to admit, like this is some of the magic stuff that I don't love about the language because I don't like it when the compiler is smarter than me and knows what, because I think you frequently get into this like, oh, well, I did it and it worked, but I don't really know what I did. And that's not cool. Rails has a lot of the same stuff, and Ruby. And while I love that language and framework, like I think that magic stuff is a little bit harder than if you learned C, where there is no magic and it is all like just hands-on, callous, creating work. Anyway, so earlier when we did, so type annotations, which is to say you implicitly saying what kind of thing you're creating, be it a constant or a variable, it's been implied. So when you said var value equals 1, it knew that 1 is an integer, and so it said, well, value must be an integer. But the reason that we might want to write them in is that for readability and clarity, it can make things more obvious. Also, when we start going into object design and implementation, which we won't do today, you have to declare the types of things in an object because it's not obvious. So sort of skipped this one. So this is what you guys were writing before the break. You would just say var value equals 1, and like I said, that's an integer. This is how you add a type annotation to make it explicitly an integer. So if I set this to 1.3, what would you expect to happen? Why? All right. Now, very good. How about that? That was actually the example that I had. So, what if you wanted to do that though? Some of you tried to add a floating point to, or a double even, to an int, and we came over and we like fixed the casting for you is the fancy word that we said. So what's casting? Casting is when you convert an object or item from one type to another. So if you take the integer value 1 and you convert it to a float, what's the result? 1.0. And is 1.0 and 1 equal to the same thing? That is what? Who said no? Okay. They are. You can give me $10.0 and $10, and I'll see how much food I can buy for myself. But this can be a lossy operation. So what happens here? So when I cast the value 1.1 to an integer, what's the output? That is correct. The output is 1. What happened to that 0.1? Yeah, I mean, so, you know, this is not always an okay thing to do, right? And also the modulus operation, so the modulus operation helps. If there was some reason that I needed to break this down into an integer and then strip that decimal point off, I could do that with mod. We won't do anything like that today. But it's sufficient to understand that when you do this, you can lose things. So let's look at another one. What's that? So if I cast 1.9 to an integer, what do I get? All right, who thinks it's 1? Who thinks it's 2? Nobody thinks it rounds for you. All right, you're right, it is. It is 1. It literally slices everything off at the, not the correct use of the word literally. It deletes everything after the period, and then that is the value that it returns. So obviously some conversions are lossy and some are not. So if you go from an integer to a float, you're not going to lose any data. But there are, and we don't talk about this either, there's, integer has a maximum, so you can only store up to a certain value inside of the integer. And there's other larger integer classes and other larger float classes, like double is the one. So you can lose stuff there as well, but we won't touch on that sort of stuff. All right. So what we've done so far is write a series of like non-reusable things. We have individual statements, we have some loops, we have some like if statements, but every time we want to test one of these things, we have to write it all from scratch, right? We don't have any mechanism yet to reuse any of this functionality. And so functions come in and let us do that. You know, generally, we try to keep things dry. We do not want to repeat ourselves. Why is it bad to like write the same code or almost the same code over and over again? Like, why would that be a bad thing? Why would it? Yeah, I mean, so like the one, even if you did it right 10 times, now when you have to change it or if it's broken, like you have to fix it 10 times. Also, you can introduce an error in one of your 10 implementations of the thing, and when you expect it to always behave identically, you just didn't notice that, you know, you missed an operator or you cast it incorrectly or something crazy happened. So functions help us do that. This is what a function declaration looks like. So this is called, in Swift, this is called the description. In C, this is called a signature. In other languages, they're like that. So they all start with the keyword func. The next thing you see is the name of the function. So this one is add. We talked about type declarations, and this is one of the reasons, because here in a function, you have to implicitly state what kind of things are going to be come in and operated upon. So the add function takes two values, A and B, and it returns an integer, which makes sense. There's some annoyances with Swift, like you can't call this with two floats. You would have to cast the floats to integers, or you would have to write an add float method that returns a float. I feel like that's something that's going to change in Swift. Like they'll start making that work a little bit better. So to call this function, I would just say, so I want to call the function and I want to store the value. So I declare a new variable named sum, and I set it equal to the output of add 1 and 2. What is sum? What type is this? I didn't put my type annotation here. How do we know it's an integer? Because the return type from this. So this is like layers of the magic of it automatically figuring this out for you that can get really confusing. If you start nesting these things real deep, it can be hard to kind of figure this out. But yes, you're correct. This is an integer. So if I said var sum int equals add 1, 2, that would work just fine. Here is a method description that does not return a value. So it is capital V void as the return type. If you do not put this arrow and then anything after it, it will imply a void. I would encourage you not to do that and to be descriptive and to go ahead and write that it is void so that we can tell you did it on purpose and not by accident. The beep function doesn't take any parameters. So I'm assuming if I call this, it just goes beep, which is a fair assumption. All right, so people had asked a little bit about objects. So objects like functions give us an even better way to encapsulate logic and things that we call properties, and to reuse that. Swift is an object-oriented language. So like a lot of the examples that I have in here are like car. So if you were going to build, a system for a used car salesman, like you would have what? Like what are some of the objects that you might find that a car salesman would care about? Right. Customers. That's a good one. Sorry. So we got customers. I'm a salesman. What do I need? Cars. Right. So maybe inventory is an object, and the inventory would contain multiple cars. And a car could have a property, and if you're a salesman, you might care about color, and all these other sort of permanent properties of a vehicle. But you would also care about its state in relationship to you. So is this car on our lot? Like, is it available for sale? Does it need to be detailed? Things like this. and we can relate to that, like as a software developer, like, okay, I get what a car is, and I get that a car could be ready for sale, and I get that, so if we use good names and we do a good job designing our objects, then hopefully our software is easier to understand and maintain. Because if you're working really, really hard trying to figure out what everything does and how it does it, then there's a really big barrier to understanding the whole problem and being able to maintain or fix or add to what is it you do. So like I've said a couple times, we're not actually going to build objects in here, although if you scream through section 2, you can certainly get to the points where you can learn how to do so. But here's some example objects. So on an iPhone or an iPad, the screen that you see, which is this big rectangular thing that you touch and displays stuff for you, and it contains lots of other stuff, that is called a UI screen. Every button that you've seen on your iPhone that looks just like every other button you've seen on your iPhone, if you know what I mean, those are just plain old UI buttons. And there's other ways to make buttons, but UI buttons are what we would use the most. Most of the time when we communicate the size of a thing, we use something called CG size, which holds both the width and the height. So CG size is designed to describe the width and height of things or describe the size of things that have widths and heights. Most usually that's rectangles. There's very few like non-rectangular things in sort of standard graphic town. You normally ended up putting them inside a rectangle anyway. And then the last one is an NSURL. So you'll notice all these objects start with 2 characters that like mean nothing, and then it's a word you've seen before. That's just the naming convention that Apple has used forever. But kind of neat. So like anything that you see with NS in front of it came out of Next Step, which was Jobs' company when he got booted from Apple a long, long, long time ago and built the Next computers and all that sort of stuff. So a lot of the classes that you use when you're programming for Apple in general are 20 plus years old, which is kind of nice. So they're very well understood and that. I mean, the UI classes, most of them are, almost 10 years old now. CG size is, 20, 30 years old. So that part's like kind of neat. So this stuff's been around, people know how to use it. Yeah. So objects have properties and methods. So if it was a car, a property of a car might be its color. Maybe a function, like a function that an object does is called a method. And I frequently mess that up and just say the wrong word. So a method for a car might be remote start. So like you call the remote start method on my phone and the car starts up. But so it's an action generally. So some examples of properties. If I had a size object, I could check its height and I could check its width, or I could set them, which I didn't show here. You can also chain these things. So a UI screen object has a size property, and a size property has a height property. So I can traverse the containment of these objects with the period operator, and this is true for functions as well, methods as well as properties. So if I have a car object, I can call the vroom method on it, which will make the car go vroom. Or in an example closer to what you'll get into next, and this is kind of clever. So has prefix is a method, and I am a string is a string literal, but Swift lets you call methods directly on string literals, which is weird, but also really, really cool. Ruby does the same thing. So if this is kind of blowing up your head, you could imagine, var string equals I am string, and then string dot has prefix, which is a method. I am, and this has prefix returns a Boolean. So it checks the beginning of the string to see if it matches the beginning of this string. And in this case, it does. So this would return a true value. And let me see, what else I have on here? For those of you who are, there's a lot of complexity that I'm ignoring right now. There's a lot of different language features you can use to create an object. So for those of you who have coded before, enumerations, structures, and objects are all things inside of Swift. There's a right time and a wrong time to use them. I honestly don't know that I was actually talking to the other guy that runs the Boulder iOS meetup last night, and we were talking about we're not totally sure when the right thing to do stuff is. Like for example, string is not a class. Like it's an object, but it's a struct. But there's a lot more reading for that, but we won't go into it too much. All right, so that's it. Try to make it up to the end of, on the second one, try to make it to the end of the first exercise there. Objective-C has it. I think it stole it from Smalltalk, if I recall correctly, which is another programming language. And we haven't used it yet. But when we start the next objects that we're going to get from the operating system and start interacting with will require us to use and understand what name parameters are. So we'll go ahead and cover it now. So this should look pretty straightforward. So I've got a method, join strings. It takes 3 parameters, and they're named A, B, and C. And so inside the method I can use them, or inside the function I can use them. But what does that method do? How? In what order? Ah, see. So at least, yeah, I mean, that's not obvious at all. So like, I mean, I wrote this and I could hardly remember that it was a little bit backwards. So the names of this are terrible. So when I call it, this is going to print out what? Equals awesome. Sorry, I like fishing. So Swift gives us the ability to, rather than just pass in parameters to a method or to a function in order, you can give them a name, which still has to be in order, but now it's a lot more clear what's happening. So if I change this declaration, and if I add a pound or a bang, or no, that's not a bang. Yeah, right, so if I add a pound sign in front of joiner, now when I call this method, I have to include the word joiner before the last param. So in this first example, we've only named one of our parameters. The first 2 are still not named. I could have done better. This could be first, last, and middle, or something like that. But yeah, so name parameters are cool. You use a pound sign in your description of your function to make it required that you pass in the name. Objects by default require all parameters after the first one to have their name passed in, which gets a little bit weird. So yeah, so we keep talking about objects, but we haven't really gotten into it too much. So when we create a new object, we use what's called a constructor. Or rather, under the hood, the object uses what's called a constructor to stand itself up, to create itself. Like for any individual option, you might have lots of different constructors that exist. You know, there's a lot of ways you can get things, basically. So we've been creating objects this whole time. Like every time we create a constant or a variable, like those end up being objects. The fact that you can do string literal dot has prefix, that's because the string literal is an object. So it behaves just like a constant or a variable, like standing all on its own. But underneath the hood, like when you're creating a string, this constructor is being called. Constructors take the form of the class name or the object name, open parenthesis, and then whatever that method requires for you to do it. A lot of constructors do take properties. So in this instance, you could create a string by calling this method. I mean, I don't know why you would do this, but you could. And under the hood, this is what's getting called for you. We talked about a size. We said that a CG size is an object that models the width and the height of something, most frequently a rectangular object. So when you're creating a CG size, this constructor requires that you implicitly pass both of the names in. So I have to implicitly say this is the width, and then I have to say this is the height. When I call to create an NSURL, which is, you know, a universal resource locator, so the location of something on the internet. That constructor requires you pass a string with the name string in front of it. You can also, here's another one. Here's another one. So here's 3 different ways to create a URL. So maybe I have a base URL. So I have brooksholler.com, and then this is family.html or something, and that will create brooksholler.com/family.html. Or maybe you want to pass in all 3 parts. So you want to pass in the scheme, which is the part to the left, so HTTP or FTP or HTTPS. The :/ will be inserted for you, then the host, so brooksholler.com, and then the path, families.html. We're not going to use all these different ways, but it's important to know that here's at least 3 different ways you can create a URL, and the output can be exactly the same. It just depends on what situation you have. Inside the playground that you guys are messing with, colors are one of the first things that we're going to play with for 2 reasons. 1, like everybody gets what a color is. 2, so does Xcode, and it knows how to show it to you. So using a color is like a good thing. I mean, it might be weird to think of, you know, a color as an object, but think about it as like a paint chip. Like you go to Lowe's, you come home, I cannot sufficiently describe that shade of seafoam to my wife to convince her that that's the perfect color for the shutters. But if I had an object, I could show her the color of seafoam that I like, and then we could go from there. So hopefully that's semi-helpful. But besides constructors, we can use other mechanisms to return objects. Frequently, this is what we would call so this is an example of a convenience mechanism where, you know, so this way, every time I call purple, I can get exactly the same purple. And so can everybody else. This is part of the standard library. So this UIColor.purpleColor returns a UIColor object. String, substring to index 3, returns a string, in this case, str. And we'll get into sort of indexing when we get to arrays. Yeah, so. Some of you guys sort of asked about code completion because you had worked on other things. Blah, 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 blah. Right, so if your version of Xcode is not automatically showing you code completion, so as you type, if you're not seeing this stuff pop up, there is a way to turn it on, but I don't remember how in Xcode 6. But you can hit escape. So you can remember that string has a sub something mechanism, you know, function. So on this string literal, I start typing .sub, and the code completion knows that that's a string object. So I'm going to show you all the names of all the functions that a string can operate on that start with the characters substring. So in this instance, there are 3. And so now I can use my arrow keys to navigate up and down and press enter. And if you hit tab after you press enter, it'll automatically jump between these bits and pieces that you have to fill in. So this makes working with name parameters a lot easier because you literally have to do a whole lot less typing. And if you type as well as I do, which is not very well, you misspell things all the time. And so code completion saves me a lot of effort. Yeah, so that's it. Off to part 2. I'm not gonna lie, optionals are funky, and it's a little bit hard to wrap your head around it. Hopefully we'll get it, but what's really tricky is sort of understanding when you would design with an optional. And what an optional is it communicates that there may or may not be a value. And so one of the ways that Apple and I like to think about it is, you know, think about it like a box. So you get a box. It's not open. So you have to implicitly look inside the box to determine if there is something in there or not. This is not a construct I have seen. This is not a construct I've seen in any programming language I have used, although there are a lot that do use it. Those are just not very popular languages. The way that we know if it's an optional or not is the question mark. So for example, NSURL returns an NSURL optional. Why? Right. So if I pass to an NSURL object, peanut butter and jelly sandwiches, that's not a valid website, right? Neither is like so if you don't pass a valid string that it can turn into a URL for you, like an empty string, it knows good and well that if you give it 0 address, it can't get there. So it makes sense that this would return an optional thing. So all of the NSURL constructors return an optional NSURL. I've gone to great pains to make sure that all of the coding you've done up till now didn't involve optionals, which is tricky because they're all over the place. When we get to the last part of the exercise and you guys actually get an Xcode or into a project, you'll have to sort of wrap your heads around them a little bit more. So how do we use an optional? So we can declare them just like we did any of our other variables or earlier, in the sense that, but we just put a question mark. What happens if you try to declare a string without giving it a value, if it's not optional? Did anybody try to do that? So if you do like var a equals, or just var a, you get nothing. You probably didn't notice, but Swift does not allow you to keep a non-optional value empty. And we'll talk about what empty means in a second. So in order for a value to be empty, or in order for a function to return nothing, you have to implicitly state that. Otherwise, it's a compile error. And so the way we do that is by testing for nil. So nil, N-I-L, all lowercase, is a reserved word that means the same thing as null, if you are familiar with null in other programming languages, and it just means nothing. But there's a difference between, so for example, is 0 nil? No, 0 is a number. It's an important number. Like, also a string that has 0 length is also not nil. Like an empty string is different than nothing. So that's sort of an important differentiation. So I can check and say, if a string is not nil, then it has a value and I can do something. So basically this line is saying like, is there anything in the box? If there's something in the box, then it's not nil. Then I can step in here and I can look inside the box, which we'll look at next. Otherwise, that box is empty. Do not open and try to use the thing in the box. Right. So once we know that the box has something in it, then we can use what's called unwrapping. So an exclamation point is forced unwrapping. What you would generally do is you would check to make sure that the optional is not nil, so it has a value inside of it. Then you would use the exclamation point to force unwrap it. So you should only apply force if you know that it is going to be okay. Optionals are added to make the language itself more safe and to encourage you to write code that in and of itself is safer. But you can write just as terrible code with optionals as you could in any other like non-optional programming language because of this last thing. Only unwrap and use the box if you know that there's something in there. Otherwise, you will get a runtime error and your app will crash. And I mean like you're using an app and then it goes away and you're looking at your home screen. That's what happens. So yeah, it's real safe. So anyway, so optionals are a little tricky. This is forced unwrapping. We look inside, hey, does this box have a value in it? Yes, it does. I use an exclamation point to get the value out of the box and then everything is fine. Our last thing, that's a lot of annoying extra code that you have to write. If you keep doing that, check an optional against not nil. So Swift gives us this mechanism, which is pretty cool. So if I have an optional string, you can write if let unwrapped equals a string. Now, what that says is, okay, look in the box. The box is a string. If the box has a value, set that value equal to the constant named unwrapped inside here. If not, skip that whole part and go ahead. So this makes life a lot easier because you can check to see if the box is empty and then get a handle to the thing on the inside all at the same time. And this over here does not have to be a variable. This could in fact be a method. And that's really, like as you see in the playground, that's when this, I think, gets really super powerful. Because you're calling a method that's returning an optional. So if that fails and returns nil, then just go on and do something else. Otherwise, take that value and then do this. So hopefully that helps a little bit. And for what it's worth, I tried to skip this, but there's no way to do anything cool on the iPhone until you understand optional binding. So there. So go ahead and let's say like 15 minutes more to work on. So one of the things that we frequently use computers to do, and games are a really good example, is to like move stuff around the screen. And there's a lot of ways that with different technologies that we do movement. I mean, first off, the human eye can only see 10 to 12 images per second. And you may or may not know, like movies, old movies, you know, now it's Wikipedia frame rates, and there's a lot of different ones, so I just picked a few. But movies historically, non-high def movies show at 24 frames per second. So this is, 2 to 2.5 times the number of images that the human eye can actually see. So since that's twice as much, we can't detect sort of the gaps in the movement and things aren't jarring. If you have a GoPro Hero or some other similar kind of like pretty nice high def camera, it might film up to 90 frames per second. If we watch things blow up on Mythbusters, like some of that stuff is filmed in the hundreds, if not thousands of frames per second. Like if you see a bullet going through an apple, well, they slowed that down pretty good. Games, video games, generally run 30 to 60 frames per second. With limitations in hardware and software, it didn't make much sense to try to go much further, but in my research on this slide, there are now graphics cards that can display up to 240 frames per second. So, still not totally sure why you'd want to do that, because that's like 20 times faster than you can see, but whatever. So why am I talking about movement? Well, because we want to make that rocket go off the top of the screen, right? So a run loop gives us the mechanism so that we can do something every whatever time unit. For example, move a thing. Most games use some sort of run loop technology, and all software now, all modern software uses run loops in the forms of threads, but we're not going to talk about that. So what happens is you have this point in your code where periodically, hopefully in a semi-predictable point of time, you call a function, and the function says, all right, well, how much time went by? And then it does all the math and whatever to calculate where things are going to go. So if this is moving at 1 meter per second and 1 second passed, then I need to move this thing 1 meter, or whatever your fake unit is. This sounds really kind of crazy and confusing, but it's not that bad. So everybody's played a board game, right? Like we play Monopoly. And so you go one at a time. You roll the dice. You move your player. You then check some state. You're on Reading Railroad. Do you wish to purchase Reading Railroad? No. Does somebody else own Reading Railroad? Yes. Do you have to give them money? Like you do this, it's your turn. You do this thing. You're now in a new state. You make all the decisions that are in that state. Did you win the game? Did you not win the game? Are you bankrupt? Do you have to quit? Like there's a lot of things that can happen in there. In games, we move objects around on the screen and then we check, did the ball go in the goal? Did the bullet hit the enemy? There's lots of things, there's lots and lots and lots of checks, and the computers make it easy for that. So what we need to do inside our little program to get that rocket to go off the top of the screen is to have a run loop. I already wrote the run loop. You just have to fill in the logic, and we'll look at that in a second. So 2 more slides. This one talks about the screen layout. So when we were in school and we would graph things, the origin was always in the bottom left-hand corner, right? So if you go up and to the right, that's X going up and that's Y going up. Even Windows does it that way, and Apple does not. Apple puts the origin in the upper left-hand corner, which is a little bit weird, I think. So this is 0, 0, and as you move this way, X, the first value gets bigger, and Y, the second value gets bigger as you go down the page. So on an iPhone 6, for example, there are 414 points across, and it's 736 points tall. And I'm not going to get into what points and pixels are, but that's the smallest unit that you can do something with is a point in this case. Last slide. So the playgrounds will run loop. After this, I'll go ahead and open up the projects as well. But if you let your Xcode project run, since we're using a timer and it will execute indefinitely, the playground will only execute it for 30 seconds and then it will stop. So even if everything is right, your app will stop running in the playground and you might get confused. Change anything, literally change anything. Just put a space in it, it'll reset and recompile it, and it'll go back to the beginning and redo it. Right, so let's see what that means. So, oh man, that's not you. That's not you. Rocket helper. All right, so so this is what you guys will be looking with, and so look at that thing. So one of the other really nice things about playgrounds is it allows you to model view things. So a button is a view, a table view is a view, a picture is a view. These are all these rectangular things that we put together to make stuff happen. So in this case, what I've done is I've created a playground that has essentially almost all the logic figured out in it that you will need for your other thing. And so now, my blue box went off the screen, so if I put a space back in, then I'll get it back. So yeah, you guys need to read over all this. There's a lot of this sort of stuff that you guys can ignore, primarily. So you see on line 27 below here is the code you copy and move to the Rocket app. You do not need to mess with this. This init statement in Rocket helper is the constructor, and it builds these guys. However, I'm asking you to, rather than to put the box in the upper left-hand corner at the start, first thing I'd like for you to do is to put the box down here at the bottom of the screen. So that'll take some math. If you got some paper, that might not be a terrible idea, or you can just play with it. We talked about rectangles and rectmake. So this is making a rectangle that's 100 by 200, and that's the red one on the outside. So hopefully you can read this and see, oh, I've got a thing that's red. Oh, that must be that thing. And then I've got a thing that's blue. Okay, so that's the one inside. So to move this guy down to the bottom, you're gonna have to change the origin of the child. So this line 22 or 21 will help you get the box down to the beginning. Scrolling down. So we have a start timer method. It starts the timer. It takes a timer interval of 1 second. You can change this to sort of whatever you want. It's a float. 0.03 is 30 frames per second, but I would keep this slow inside inside the playground. Otherwise, it'll go really, really fast, and the thing will jump off the screen probably. We have a stop timer, and then we have timer fired, which is so these guys. This starts the run loop, this ends the run loop, and this is the run loop. And I won't go into exactly how all that is, but when we start the timer, we tell it what to do when the timer fires, and this is the name of the method that gets executed when the timer fires. So right here at line 57, the class that I declared to help ends, and now we're back into sort of regular playground code. So I create myself a Rocket VC helper object. XCP show view is a special playground mechanism, and that's what's doing this. It's what's showing you this window without using the magic eyeball. And then in order to get the run loop to start, I have to call start timer. Great. So that's the playground. So now if we look at, oh, it's so hard. So now if we look at the rocket example real quick. Hopefully this is not the one that's finished, because that would take all the fun out of it. It is. So let's not look at that one. So all of the, oops, this is it too. Oh, I did after. So you should also open and look at the Xcode project itself, or I'm sorry, the iPhone application project itself. If you can't see this over here, I can come by and help you find it. But everything you want to touch and change is in viewcontroller.swift. And same thing, I've sort of tried to call out in here what you need to mess with and what you don't. So on line 52, we have insert code below here, and you'll see essentially the same three methods that you see in the playground, which is starting the timer. So all the logic to start a timer is missing. Like I did go ahead and do this running thing because I do a switch based on whether or not it's running. That's different from the playground. So then when I reset, I need you guys to write that, which is very similar to the stop timer. And then here I have the instructions for inside your run loop, what you need to do to help move your guy around. And I wrote, you do it by calling a method basically that I wrote for you up top. So you figure out how much it moved and you call the move ship up. So I've already done the work of figuring out, like, so you don't have to rewrite the actual logic to move the ship unless you speed through this real fast and you decide, oh, I don't want it to go straight up, I want it to wiggle. Cool, we can do that. So there you go. So we've got 30 minutes to the end of the class to sort of try to figure out as much of this as you can in the playground and then try to get it, learning what you've learned. Using what you've learned, come over here and try to get this guy wired up. If you blow through this and you get it done real fast, I have a lot of other ideas for what you can sort of do next. There's a whole bunch of other images that we could add in, so forth and so on. But I think it'll be pretty good to get you guys to this point by the end. So that's it. Go forth. So once you make changes to your code inside the iPhone app, rocket.xcode project, you need to hit the build and run button in the upper right hand corner. You can also press Command B. That'll do the same thing. So now if I hit play, what I would expect to see, since this is the blank project, it'll build, which every time you change anything in the playground, that's automatically building and running. This you have to explicitly build and run. And now I have my application, and I know it's cut off this screen, and that's the best I can do, but if I click on that button, nothing will happen because it isn't wired up. So hit run to make it go, hit stop to make it stop, which is the button next to it. Over here you can change what device it goes to, but you shouldn't need to. So yeah, sorry I left that one out.